So this last section of this chapter is geometric sequences. A geometric sequence is just like an exponential function, and that's basically all we're trying to get out of it. So with an exponential function, we multiply by the same number over and over again to get the next one. With a sequence is just basically a list of numbers that have a pattern to get to the next one. And so if you look at this one, I multiply by 3 to get 3, multiply by 3 to get 9, multiply by 3 to get 27, and multiply by 3 to get 81, and so on. And so just like with exponential, we're multiplying by the same exact number every single time. And so then the next thing we need to understand is notation. Now we're going to be seeing a lot of a sub n's. And what I mean by that is we can have an a sub 1, an a sub 2, an a sub 3, an a sub 4, and so on. And that's just basically saying which number in the sequence you're looking at. A sub 1 is the first number. A sub 2 is the second number. A sub 3 is the third number. A sub 4 is the fourth number. And so sometimes they might ask you to find a sub 5. So you're just trying to figure out what is the fifth number in the sequence. So we'd have to figure out the next one there. And so when we use this notation, we also have a different way of writing the equation. You're used to seeing the equation being written as y equals a times b to the x. Now a is the initial number when x equals 0, so our initial value, and b is our loop-de number, or the number that we multiply by all the time. Now instead of b, we're going to start using r. This is our common ratio is what it's called. And so whenever you see an r, you know that it's common ratio. It's our loop-de number basically, or the number we multiply by every time. However, this number at the beginning, we're going to have to kind of be a little bit delicate with how we work on that. So, normally it's y equals a times b to the x. Now, if we did the exact same thing as what this does, we would have a sub n equals, instead of y, it's a sub n. And then remember, a is when x equals 0. And so we would have to use a sub 0 here to say our initial term is when x equals 0, so we would have to have a subscript of 0, which is actually not in our list. The very first number is a sub 1, so that causes a little bit of problem. But then we could use times r to the n. Instead of x, we use n here, because that's kind of our unknown. This would be really nice if we could use this formula, but what typically happens is we use a sub n equals a sub 1 times r to the n minus 1. And so what they're doing is they're saying, since I normally have a list like this, and this number right here is a sub 1, it's kind of weird to be using something like this where we have a sub 0. So instead we use a sub 1, meaning, if we were looking at our table, normally we want to know when x is 0, but now what we have is we have this, and we don't have this one right here basically. We don't have our a sub 0. So we don't really want to create an a sub 0. So then what we do is we use a sub 1, which means now this right here cannot just be an n, because if it was an n, then it would always have to go back to when x is 0. So we would have to subtract 1 from our n to say that we're going back a loop-de, kind of. I don't know. To say we're going back a loop-de, I guess is about all I can tell you. So let's say that we have this problem right here, the 1, 3, 9, 27, and so on. We would write that function as a sub n equals, the very first term is 1, the r is 3, and then that's going to have to be n minus 1. Now if you really don't like that, and you want to be able to write with just an n, then we would have to write a sub n equals, and we have to go back 1. So, normally we'll multiply by 3. We're going to have to go back 1. We're going to have to divide by 3. So our a sub 0 then is 1/3 times 3 to the n. So let's talk again about this one. If I didn't have that n minus 1, see, if I plug in, if I want to find the fourth term, let's say, I'm going to have a sub 4 equals 1 times 3 to the, and instead of being a 4 there, it's going to be minus 1. So now 4 minus 1 is 3, so 1 times 3 cubed would give me 1 times 27. So apparently my fourth term is 27. And if we look, we've got 1, 2, 3. My fourth term is 27. Problems that we could see are we want to find a sub 6 if a sub 1 equals 2 and r equals 3. So we could do this a couple ways. We could start, well, a sub 1 is 2, and then I have to find my sixth one. This is 1, 2, 3, 4, 5, 6. And I know I'm multiplying by 3 every time because r is 3. So then I just figure that out. 2 times 3 is 6, times 3 is 18, times 3 is 54, times 3 is 172, I think, times 3 is, I don't know, 516. So then a sub 6 would be that. My other route I could go is using this formula. A sub 1 is 2, r is 3, and then remember now, because it's not a sub 0, it's a sub 1, I'm going n minus 1. And then to find a sub 6, I go 2 times 3 to the 6 minus 1, which will be 2 times 3 to the 5th, which will be 2 times 3 to the 4th is 81, 81 times 3, 243. Multiply that by 2. Wow, I was really off up here, wasn't I? Anyway, 6 times 4 is 8, 486. Oofta. And then another one would be if you have this sequence, we need to find r. So we need to figure out what are you multiplying by every time. Okay, now sometimes it's hard to tell. So you might have to actually do some math, and what you can do is you can take the second one divided by the first one. So if I take 90 divided by 100, I get 9 over 10, or 0.9. And that would be then your r value. And then you want to check that. You want to check that 100 times 0.9 is 90, and 90 times 0.9 is 81. But once you've checked that and made sure that it actually works out, that would be your r value then. So remember, it's your second number divided by your first number, and that works no matter where you are. You could be your second number here divided by your first number here, and you'll still should get your 0.9.